Welcome to the 2025 Gardner Lecture. I'm Julie Shaw. I'm the department head here at AeroAstro. And this is a very exciting event that we hold each year. And so thank you so much for all coming out to be a part of it. The Gardner Lecture is made possible by a bequest of the late Major Lester D. Gardner, a member of the MIT class of 1898, to sponsor annual presentations on aeronautical history. He was an air officer in World War I, and he was the recipient of numerous aeronautical awards, including the Daniel Guggenheim Medal in 1947, given for the citation for outstanding achievement in advancing aeronautics. He had a long and storied career. He established a publishing group that's responsible for a number of major aeronautical trade publications, including the predecessor to Aviation Week. And he was also the founder of the Institute for Aeronautical Sciences, which eventually evolved to become our AIAA. Major Gardner's interest in MIT and our department continued throughout his life. And it lives on not only in this Gardner Lecture, which is a big important event for us in the department, but also in the Hunsaker Professorship, which he helped to establish. And in his honor, we continue the tradition of hosting the Gardner Lecture to celebrate our history in our field and to keep looking ahead by looking up. And so over the years, our Gardner Lectures have included Grover Loening, Igor Sikorsky, Yvonne Brill, Neil Armstrong, Robert Siemens Jr., John Langford, Pam Melroy, just to name a few. And so with that incredible history under our belts, it's my great pleasure to welcome and introduce this year's Gardner speaker, Dave Limp. Dave is CEO of Blue Origin, a private space company founded by Jeff Bezos with a vision of millions of people living and working in space for the benefit of Earth. And as you all know, the company builds reusable rocket engines, launch vehicles, in-space systems, and lunar landers. So Dave joined Blue Origin as CEO in 2023, and he also serves as the board chair for Blue Origin's Club for the Future, which is a nonprofit organization dedicated to inspiring and mobilizing future generations to pursue careers in STEM. Dave has previously been at Amazon since 2010, where he oversaw the development, retail sales, and operational aspects of Amazon's consumer electronics devices and the services behind them, including Alexa, Echo, Kindle, Fire TV, Ring, just to name a few, as well as other initiatives such as Project Kuiper. And many MIT alumni have gone on to work at Blue Origin. And we've also had quite a few research payloads launch on Blue Origin's New Shepard rockets. So with Dave at the helm, Blue Origin is exploring increasingly ever more exciting missions and aerospace engineering challenges that are truly at the cutting edge of spaceflight. And he's here today to tell us all about it. So please join me in welcoming Dave.
Thank you. Thank you, Professor Shaw. I hear the previous speakers on this, and the quote from Wayne's World pops up in my head that I'm not worthy. So I'm going to do my best to give you a little words. Hopefully, they inspire you in some ways. This lecture series goes back to 1959, and it's just an amazing honor to be here. I want to talk today about how we as a collective species, and specifically this class, and you all, given your focus on aerospace, can help build a road to space. And this is a big, really important mission in our mind, and one that's going to take multi-generations to do. But it is critically important. And so to plant that seed, I'm going to start with a quick video, and then we can talk about something that is seemingly small, but is the seed that plants this very, very large vision.
Holy cats. Weightlessness. Oh, Jesus. Oh, my God. Oh, wow. I can't believe this. Everybody in the world needs to see. There is Mother Earth and comfort, but what you see is black. Oh, God. I hope I never recover from this. I hope that I can maintain what I feel now. I don't want to lose it. what you have given me is the most profound experience I can imagine. I'm so filled with emotion about what just happened. Jesus. Oh my God. It was unbelievable. Oh, I'm telling you.
What you saw Bill there, and there's been over 700 people that have gone above the Kármán line and had their version of this. I've been super lucky to meet a number of astronauts, a pretty significant number, and Julie and I have seen a few of them in some of the same conferences. And to a T, I haven't met them all, but to a T, they all have a similar story to what you just saw Bill have. There's actually a name for it. It's the overview effect. And everybody comes back from space changed in many different ways. But one common thread is this overview effect. And it's the sense that as soon as you leave the atmosphere, you see how thin of a line there is protecting this great planet Earth. And then you look up and you see the deep darkness of space and see how vast it is. And you come back with the feeling that Earth is small, Earth is fragile, and Earth should be protected. And we've sent, and with lots of people in this room's help, probes to all the moons, most of the moons, all the planetary bodies we've crossed. And rest assured, the Earth is the good planet if you want to live. And we know that now. And so our purpose is to figure out how to think about that in that context and preserve that which is the Earth. And to do that, we have to think about what has happened over the past couple hundred years. If you go back a couple hundred years and you think about almost every metric that we would measure prosperity by, life expectancy is up from 40 to 75 years. Infant mortality has decreased from 175 deaths per thousand to less than 28. Global literacy is at an all-time high, highly correlated to prosperity. Poverty rates are below 10%. Hunger is at an all-time low. I could go on and on and on again, and you would find reasons why our lives are incredibly better than they were. There's one notable difference, though. That notable difference is I can't go down to the Charles River, ladle up a good scoop of that water, and drink it. We've paid the price of all this prosperity by using some of the natural resources that are on this Earth. By any dimension, it's more polluted. We could argue how much warmer it is, but the fact of the matter is, it's still the great planet. And our job is to try to figure out how to preserve it. And this is the foundation of our mission statement, which is, in a simplified way, we want to take the polluting industries and move them to space. And then we can rezone this great planet of ours, Earth, to parks, recreation, maybe a little light industry, roller coasters, you name it. But it's going to be a place that you can come back and visit. Some people still live here, and we'll be prosperous in space and preserve that which is the thing we love about Earth. So for the next 20, 25 minutes or so, I'm going to try to paint a blueprint of the infrastructure, the key pieces, and they're not all of them, they're not all inclusive, but some of the key pieces that we think are critical to invent to make this a reality as we kind of move forward. So the first thing I would say is that space, to get this to happen, space needs fundamental infrastructure. And if you think about the building blocks of any step function change, as you think about how to get to a big vision like this, it is the infrastructure that you actually think about. I have a front row seat to this because I've spent a lot of time with Jeff, and Jeff tells the story of this in the context of Amazon. So let me tell you that story about Amazon. Jeff started Amazon in a garage in Seattle. It's just him, a couple other people. And yet now you look ahead and it is your new normal. What would you do without it? How would you get packages delivered to you? How would you do this? But how does one or two or three people do this in a garage? It's because they had infrastructure that they could rely on. They were standing on the shoulders of giants. They didn't have to build an entire transportation network. There was UPS, there was FedEx, there was the postal system. They didn't have to build new payment systems. There were credit card companies, Visa, MasterCard, American Express, all those existed, so you didn't have to go build that. You didn't have to build that which was the internet. That was on the backs of DARPA and Xerox PARC and a lot of other research institutions that had built this infrastructure to be able to move bits around. And so the young entrepreneur that was Jeff at that time could focus on building the application layer, knowing that all that infrastructure existed for him. And we want to do the same thing for space. Build that infrastructure such that when your kids, it's likely a multi-generation thing, wake up and decide, gosh, I want to do X in space, they can take it for granted that all the hard, heavy lifting is there and focus on the application layer of what they want to bring to market. So, what do we want to do? I'm going to give you a couple different infrastructure pieces, selfishly that Blue is working on, but there's lots of other people working on this as well. The first is we have to dramatically reduce the cost of launch. Specifically, dramatically reduce the cost of a kilogram of payload to the orbit of your choice. If one of the hardest things here is, in fact, getting payload to space in an affordable manner. Now, we've done this as, you can go all the way back to the Apollo program, and we got a lot of mass all the way to the moon. It came in an incredible cost. At the peak Apollo, it was spending, there's different estimates on this, but spending about 2.5% of GDP per year. That is an unfathomable amount of money. Give me 2.5% of GDP, I will give you fusion in 10 years, okay? But it's not gonna happen. And even at the end of Apollo, the American people got fed up with it. It was too much of a drag on the economy, and it had to be slowed down and eventually shut down because it's unsustainable at those rates. But you can do amazing things in space if you have the ability to do this. So our job as this industry, and certainly at Blue, is to how to take the amount of price of that kilogram to orbit and bring it down. And you can start seeing this on a curve. It's a logarithmic curve on dollars on one axis and then years on the other. And you can start seeing where the knee in the curve happened. And specifically, where that started happening is when you started to see the introduction of reusable rockets. When you get in your car, and you drive from point A to point B, you don't throw away your car into the ocean at the end of the trip. Similarly, when you get on a Southwest Airlines and you fly to point A to point B, they don't scrap the plane. Yet for the last 50 years, except for the last 10, that is how we treated rockets. We just got rid of them, they were disposable. And so reusability is a key. And Professor Shaw mentioned that you've seen some of this in some of your classwork because we have a suborbital reusable vehicle. And it's incredibly profound that things like this are our new normal. Just 10 years ago, this was the thing that science fiction was made up of. That the idea that we would be landing rockets literally every other day or every third day right now, orbital, suborbital, is just an amazing and profound change. And this reuse is completely new. And it changes, on the booster side, it dramatically changes the formula. And as we start thinking about getting reusing second stages, it furthers that formula. And you can see us continuing to climb down that curve that I showed you. I know this is something that you in course 16 have been studying a lot, and you've put payloads on this, so it shouldn't be new to you. But it's dramatic in its ability to help us down that cost curve. The second part of the cost curve, anybody know what this is? No? Rocket formula. There you go. Okay. Extra credit for you. I have no grades to give, but you get it. So this is Solowski is often credited with this. I think there's some controversy that it might have been more, but anyway, this is a very famous formula that tells us a lot about delta V, but one of the most incredible things that it says is, it's a function of wet mass over dry mass. And it leads you to a lot of different conclusions. The one I'll focus on here today is that it leads you that rockets want to be bigger. As rockets get bigger, that mass fraction changes, and every extra amount that that fraction gives you, we can move to payload. Assuming we're massing out on payload, you could argue that some payloads volume out. And so we want to be able to do that. And that is where the industry is moving. We're moving to ever larger rockets. It was another place, it's kind of amazing how much the Apollo engineers had right. I'll talk some more about that later. But large rockets have incredibly good mass fractions. And you can start seeing that in the percentage of the propellant that goes over the payload. And our rocket, which is New Glenn, our big rocket, which we launched earlier this year, got to orbit, haven't landed it yet, but just hang on to your hats, coming soon, is an incredibly large rocket by any measure that we would have been talking about just 5 or 10 years ago. It's 320 feet tall. It can throw 45 metric tons to LEO orbit, which is 13 metric tons to a high energy orbit like GEO. So this is an incredible workhorse, but more important than that, it also has a completely reusable first stage. We launch from the Cape, we land out on a barge about 300 nautical miles offshore, we barge it back in, we refurb it for a couple days, and then we go ahead and try to fly again. And it also has, I talked about that mass is important, but increasingly the amount of volume that you can put up as well. It gives you more flexibility to design the payloads. So our fairing size is 7 meters. So to give you a sense of the size of that fairing, New Shepard, which I showed you land earlier, with the nose cone on it, can fit into the payload fairing of New Glenn, to give you a perspective on the size of this vehicle. And it's powered by 7 BE4 engines that are Methlox engines and optimized for the atmosphere. And then the upper stage is powered by BE3U engines, which are very high efficient and optimized for non-atmospheric work. So these are incredibly powerful vehicles. And when you get to this size, again, you start seeing the cost per kilogram of payload come down. I would be remiss to talk about New Glenn without at least showing a launch. So there we go.
I think it's a big day for a lot of us. A lot of us worked many, many years, put in a lot of blood, sweat, and tears to get to this point, and it's a very, very awesome day.
I'm very excited for the world to see what Blue Origin is capable of.
I'm most looking forward to seeing us safely reach orbit, and I'm excited to celebrate it with my team and my wife.
OSM LD set hold fire switch to launch position. Lift off.
All 7 engines at full thrust.
Continues to perform well. Now passes to Max T. Max T by bonus pressure.
And we have ignition on both BE3Us. Chamber pressure is good. GS2 is now working.
As soon as we saw liftoff, we were like, oh my God, we did it.
We got to orbit. What an incredible rumble from the B4 engine.
Yeah. Never gets old. You just got to do it over and over again. I also love the thing about that video. I love is the BE4 team is like they see Miko and they're just like, we're done, we're out. Meanwhile, that BE3U team and the upper stage team is just like sweating bullets trying to get to orbit. It's okay though. So what have you done for me lately? It's great. So we talked about reducing the cost of mass. That's the first critical infrastructure thing that we have to think about. The second critical infrastructure thing I would postulate is how do we build a hydrogen space economy? So why do we want hydrogen? Well, there's a lot of reasons, but some have come very true to fruition in the very recent time, which is with the latest exploration that's just, again, all come about in the last decade or so, is now we have very high confidence that water is on many parts of the moon and also on Mars. And this means you can just crack H2O and we can get both the fuel and the oxidizer from hydrogen. And being able to get that, if you just go back to the rocket equation, the mass fraction would tell you, for all the things that make this Earth great, the atmosphere is pretty good. I like it. Gravity, 1G, kind of like 1G too. But it's pesky for rockets. So every time we have to bring fuel up or oxidizer up, it's just mass that if we could build it in space, it's so much better. And so knowing that we now have water on Earth, on the moon and Mars and likely elsewhere gives us high confidence that hydrogen was the right choice. But again, I go back to the Apollo era, and they had it right again. It's amazing how a bunch of folks using slide rules had so many design decisions right, but this is another example of that, which is that you really do like to have a carbon-based first stage engine. In our case, we're using liquid natural gas. And it was back in the Apollo days, it was a different propellant, because you have such good density from it. So you can pack a lot more in your tanks, and while you're fighting the atmospheric and gravitational drag, you can go ahead and get through that. However, when you start getting to upper stages and you're not fighting those forces, you want to try to get something that's much, much more efficient. And when you think about ISP in an engine, the actual specific impulse of the engine, there's really almost nothing that beats the ability to put hydrogen and oxygen together. And it just makes sense. And so we have chosen that for those reasons. Now, there's obviously downsides to this. I can make a lot of arguments about why you wouldn't want to do this, not the least of which is they're entirely different engines, which entirely different cycles. And so the logical choice, if you're running a business, is to just say, okay, I'm going to take my atmospheric engine, and I am just going to optimize a vacuum version of it, and I'm going to call it a day. It's less test stands, less infrastructure, less ability to have things go wrong. But the right answer, architecturally, to create a hydrogen economy is to have optimized hydrogen engines. And we do it in, not only in what you see here, which is this is the BE3U, that was the upper stage engine you saw in the video, and there's 2 of those on the New Glenn vehicle. But we also have a secondary hydrogen oxygen engine, different cycle, smaller, a 10,000-pound thrust engine that's we're developing called BE7 that is available, think of it as the intersolar system engine to get you around. So it will it'll fly our transporter to the moon. It'll power our lander to land on the moon. And it also uses hydrogen for all the same reasons that it's readily available and incredibly good in terms of performance. So what's the other downside of going to hydrogen and oxygen? Well, they're stored at cryo temperatures. And cryo temperatures have this pesky thing they want to boil off. And we can insulate them, we do, and we can, but for longer duration missions in space, traverse to the moon, starting to think about traverses to Mars, that boil off as a percentage of, you can see the numbers here, as a percentage of where you are, starts to add up pretty quickly. And so you want to figure out how are the ways that you can mitigate this. Again, insulation helps, but in itself it is not enough. And so, again, thinking about what do you have to build to do this hydrogen economy, it comes back to what do you have to invent. And so in this case, you want to invent a cryocooler. And so zero boil-off cryocoolers. By the way, cryocoolers are not anything that's brand new. If you ever see somebody with heat fission goggles, they have a version of these kinds of things in miniature Stirling engines and things like that inside of them. But when you want to do this in space, it's just never really been done before. And you're talking about liquid hydrogen, liquid oxygen, and you need to store them at very, very low temperatures and in a vacuum. So this is one of those things where I say when I got to Blue 18 months ago, I was worried about this invention. It had never been demonstrated. But we hit our NASA milestone about about 2 months ago or so. And we, on Earth, so we still haven't done it in space, but it was in vacuum on Earth. We demonstrated that we were able to, in vacuum, keep at 20K and 90K. Those are the stable temperatures that we need to keep liquid hydrogen and oxygen from boiling off. And so it's a huge milestone change. Again, hard problem, but if we can knock down these hard problems, we can actually get the incredible foundation of this hydrogen ecosystem in space. Okay, so we talked about reducing the cost to space, at least to orbit. We've talked about building a hydrogen economy. Third, I would postulate that the moon is our strategic gateway. And this may not be the common wisdom across all space companies, but it is ours. And you know, I don't know where you all fall down on the Fermi paradox, but if you're in the simulation camp, the moon would be a cheat code. I mean, who would possibly put this body 3 days away from Earth, no atmosphere, with asteroids and meteorites hitting it for millions of years, guaranteed to have every element known to personkind on it? It's just like you would never have guessed something like this could possibly have happened. But indeed, it is there, and I don't think we're in a simulation, so we're going to use it. Okay, and like it's our mine, our resource depot 3 days away, and it's incredibly rich in resources, and it's something that we really want to do. So a lot of what we're doing is thinking about going back to the moon, but it's not just about going back to the moon. In fact, our lunar team is not called lunar; it's called lunar permanence. We've been to the moon. We've been there and back a few times, a dozen times, but we didn't stay. And that was an amazing accomplishment, by the way. Probably fast-forwarded the moon 20 years, the Apollo program, if not more. But now you want to go there to stay. And you want to go there and be able to use the resources that are up there in clever and innovative ways. So how are we doing that? Well, we're going to do it in 2 steps. This is the original Apollo lunar module, the LEM on top of it. Our first vehicle that you see here is our Mark 1 vehicle. It is in final assembly right now. It's just about to go off to vacuum test in a little bit. And it is a cargo lander, and will go to the moon, first quarter of next year, probably, in that range. And it will be the biggest vehicle to have ever landed on the moon. It's also we're not going to make it easy. We're going to do a triple Lindy here. We're going to land it near the South Pole of the moon. So it's a big effort for the team. But just to put that in comparison, then contrast it to what we call Mark 2. By the way, Mark 1 we just won a NASA contract to take Viper to the moon. So it'll be serial number 2 of Mark 1. We'll take Viper to the moon. And then next to it is the human-rated Mark II vehicle. We're also doing a cargo version of that. But to give you a sense of the scale of that, it's 15 meters tall, 30 metric tons to the lunar surface. So this is the semi-truck that is going to be able to pull lots of cargo down to the moon to allow us to get that permanence and begin to plant the seeds for a permanent base there that we can then again mine the moon and begin to build the infrastructure there to hop off to the rest. And so you can see a credible amount of difference in mass from where the Apollo mission were up till, might be a typo, I think it's 30 metric tons, but I could be wrong. So what do we have to do to make the moon more interesting in terms of infrastructure? Back to the same things. This is going to seem very duplicative to some of the students that presented to me earlier on your own class project, or I guess NASA project for being able to navigate autonomously on the moon. We're going to have to build vehicles that can traverse the moon. Some are going to be to do mining, some are going to be to do exploration, some are going to be transport. And the first stages of this are how do we build a rover that can be able to do this? And I know you guys, the Maple team, which I saw present earlier today, it was just great to see the progress you made. Second place is a huge achievement in this, and I was sitting there biting my tongue because I know how hard a problem it is because I meet with this team every 2 weeks and get a sense of what's going on. So our effort here is to start taking payloads up to the moon. Our first one will be on Firefly's next lander. We're doing our Honeybee team is doing the rover, And it will be a traditional rover in every sense of the word. It's lower cost, but it will be teleoperated and be able to be teleoperated. But we're in parallel with that going to put a complete autonomous package on it. So that we in parallel can run experiments about what does autonomy look like on the moon, so that vehicles after that and after that will get steadily more advanced as we move through. And I think, again, it was one of those things that was shown very, very, in very, very good detail earlier today. But having worked on autonomous vehicles for a lot of the last 10 years of my life, Zooks was in my team at Amazon. Much of the problem of getting autonomy working is a data problem. That's why when you go around San Francisco, you see lots of Waymo cars with a driver in it with sensors on it, or Zooks cars. They are training up the road systems and getting data and understanding what are the anomalous things that happen in traffic. Last time I checked, we don't have those on the moon. And in fact, you could say, oh, but wasn't Apollo up there with a rover? Yes, but the cameras, not so good. They were running, I think there's like 7 hours of true video, but when you back it off, it ends up being about an hour because it was running at 12 frames per second, but only took a snapshot every so often. And so we do have that data, but it is not representative of what you're going to see, especially at different parts of the moon as you get to the poles. Obviously, the lighting conditions change dramatically, and you can be in night for a long period of time. You can be in sunlight for a long period of time. And so the navigation challenge becomes incredibly complicated. And so what we're able to do through simulation, this is actually a game engine running our lunar terrain scenarios internally, and we can then do a digital twin of what a rover looks like. And we can try different sensor packages and say, I wonder if it'd be better with stereo optics or it'd be better with LiDAR. Would it be better if we had a really good IMU, or should we figure out a way that the lander has really, really interesting beacons and use trigonometry to figure the problem out? There's lots of different ways you can solve this, but it turns out to be a pretty tractable problem, and we are very excited about where we're going to get to here. The other thing about the moon, I talked about how resource-rich it is that you don't have to go very far. I kind of was implying that you could dig and you'd find platinum here and gold there and unobtainium there. That's true. I'm very big an optimist on that. But the regolith itself is incredibly rich in resources. So we have a whole different team called Blue Alchemist, again, infrastructure, figuring out how to build reactors that can be powered on the moon, but that you can just put in one side of this robotic reactor, throw the regolith in it, and literally out the other end is going to come a silicon solar panel. And this has been proven in our labs already in the piece parts, and we're now in the formulation stage of putting that all together. And in our labs, these are in California, we're getting purities of silicon at more than, I guess, 3 or 4, 5 nines at this point, 99.999%. So this is incredibly optimistic to be able to now create power on the moon. And once we crack silica and that, the refining process actually works across a lot of different types of things. So the more we find out about regolith and what's there and one layer below, the more this on-premise, on lunar ability to be able to get rich resources is really going to be game-changing in a sense of infrastructure. Again, it's just less payload you have to bring from Mother Earth. The final thing I want to talk about in terms of infrastructure, we've talked about lowering the cost, hydrogen economy, use this cheat code of the moon as a stepping stone, is building comms infrastructure. If there's anything we've learned on Earth is that comms, communications infrastructure, is incredibly important. The amount of just exponential growth in both free speech and the ability to understand what's going on because we have open comm systems and effectively unlimited bandwidth in lots of parts of the Earth has changed how we think about our social life. It certainly thinks about how we change about our work life. It changes productivity. There's no reason to believe that that's not going to be true in space as well. And if you look at the infrastructure in space today, again, not taking anything away from the amazing engineers that put the infrastructure that's there, it's aging. The infrastructure around Mars it should have been died many years ago. What's around cislunar is aging. What's even in the upper parts of Earth orbit is aging in many ways. And so we believe that you have to think about how do we build the Internet of Space? How do we lay that infrastructure? So again, that entrepreneur that's coming in the future just knows comms is free, or so inexpensive it rounds to free. And so one of the things that we're thinking about to start this is building, we have a satellite platform that can be used for lots of different esoteric orbits. It can be in GEO. This example I'm showing you here is for the Mars Communication Orbiter, or MCO. So we would take this is a 20 kilowatt satellite bus. It has a credible delta V, 4,000 meters per second of delta V through both chemical and electrical propulsion. And we would send this to Mars. It would sit in Mars orbit. Then you can see it shed off a bunch of little baby satellites because it has a lot of payload that would circle Mars. Think of them as the Kuiper constellation around Mars. And they would then call back to this hub, which is highly powered, and it would use laser communications and RF communications to get back to something in LEO orbit on Earth or a ground station, depending on what we do. And then you can then stamp these out. You can do a few around cislunar. You can do one out in GEO. You can communicate down to these proliferated LEO constellations like Starlink or Kuiper. And you begin to start seeing an architecture where you, as an entrepreneur, have this amazing comms capability, just like you have if you plug into your Wi-Fi that's kind of right around the corner. This is a sense of the kind of data bandwidth that we'll be able to change, and it's an order of magnitude at least. I think we'll actually do a little bit better than this as when you can start thinking about this. And the first advantages here is not going to be that young entrepreneur. Like I said, that's multiple generations away, but it's going to be science. And we're going to learn more about Mars. So much is throttled today about what we can put down on the surface of Mars for payloads or on the surface of the moon. And more bandwidth we have, the more science that can be done, the more we'll understand about these bodies as we kind of look through this. So I'll just finish just summarizing a few of these things that if you're going to go and build a place where millions of people can live and work in space, you have to start somewhere. Somebody asked me this question earlier today at lunch and said, well, where do you start? And I would postulate what we talked about here today is where you start. Start with the Lego building blocks that are infrastructure. And if you start there and you do it well and get other companies to do it well, then generation after this or the generation after that will help a lot. My team would kill me if I just stopped there. So I'm going to give an unbelievable pitch for MIT. Despite not going to this university, I'm still going to give a pitch. We have incredible people. I know a number of you have done internships. Thank you for that. If you haven't done an internship and you want to do an internship, please, that would be great too. But some of the faces that you see here, Jordan is the first one up there. He runs all of New Glenn, and he is an MIT graduate. Henry, who runs the entire second stage and reusable and fairing program, MIT graduate, and his son just was one of the 10 most recent invitees to be astronauts for NASA, so that's kind of cool too. And I would just say that I'm biased. I'll be the first person to say that, but I love this company. It is so missionary. I told Jeff I would do this for free for him. Luckily, he didn't take me up on that. But every little bit of it, I go to work with a smile on because of what I really do think what we're doing is helpful for the planet, and it's very cool. And so often, having worked in and around technology for 30 years, when you don't often find the Venn diagrams that intersect there, where it's awesome, cool technology, and you just have a ball doing it. Sometimes it's laborious, or sometimes you trade those various different things. So I want to thank you for that. And before I go to Q&A, I did want to ask Professor Shaw to come up as well. We've been thinking about this relationship from MIT for a long time, so much so that every once in a while on New Shepard, we fly a pennant to space. And this one went up on our first flight. And so there's not many from that flight, but we wanted to present it to MIT as a thank you for the partnership, okay?
It is an honor.
Yeah, thank you.
Look forward to continued partnership.
That's awesome. Thank you so much. I appreciate that.